There could be many times in our life where we encounter graphs like this. YouTube videos where they feature graphs that look like this. Or describing the length of a line where its endpoint touches this part in your ruler. With using our own two eyes, we could say that those values in there are actually undefined, and we even tend to guess its value. However, if we use a different perspective, our perceptions could be changed, as this point of view certainly gives its approximate value with a definite basis on how did we get it. This perspective has a lot of applications and uses, especially in an undefined value in a function. Ladies and gentlemen, let's all have our next episode in Calculus Begins, Limits. Whenever we hear the word limits, we may actually think of a few things. At most cases, we would firstly imagine that speed limit as we cross the road. Others could be also imagining that limit we set in spending our money. The money that we actually have to divide for the essential things we have to purchase down to the least concerns or wants. It could also be that limit you set on spending time with your activities of a single day, such as with talking to your friends, exercising, playing games, reading some books, then to having quality time with your parents and family. Lastly, it could also be that limit we set on foods we shall eat if we want to gain something or if we want to maintain a healthy diet. We shall be eating less to achieve these things. Now, among all these thoughts we just generated, the limit that we are actually talking about today certainly does almost the same thing. The limit exists to make us gain something, an approximate value of a function when it is undefined. These limits tell us how does a function acts near a certain point but not at that particular point. Because at most cases, the particular point is actually undefined. Its role is also to warn us that it is approaching some value, which the limit is aware of, and not us, because we still have to find it out ourselves. Just like how we pass a speed limit on the road, because we may not know what's going to happen next after a few miles. Limits have a lot of applications in this regard. We may be using them only in mathematics, but you don't know that you're also using them in other things. First and foremost, you may never have realized you were using limits as you were trying to round off a certain number when it's written on a decimal form or not. Let us suppose the value is 10.11. That's going to be the value of A, or the actual value when we talk about the limit. But your teacher decided to round off that number to a whole number. The value then becomes 10, and so 10 is considered the limit of the function. Another supporting case to this is that calculators may give you values of pi that mostly display 8 digits, while others show much lesser than that. Yet, people who found to solve the value of pi have interestingly provided a multitude of digits, which reached billions and trillions, especially during the past 2 years when Emma Haruka Iwao, a Google employee from Japan, breaks the world record for calculating the value of pi to 31 trillion digits. But teachers only use the rounded off value of pi, which is 3.14. That's because we do not know the full value of pi, or that 3.14 is the standard and the generally accepted value of pi. And whether we would use 3.14 or 2 more digits after 3.14, it's still going to generate the same value, or at least closest to it. Other applications of limits include an example from Hazel Ali from Prezi 2017, where he or she stated that in a beaker where a chemical reaction starts with 2 chemicals that form a new compound over time, the number or the amount of the new compound is the limit of a function as time approaches infinity. Well, when we say as time approaches infinity, this means that values may grow larger or smaller as time increases. It could be that amount of the new compound that may increase as time progresses. Also, it applies to a situation where you drop an ice cube in a glass of warm water and measure the temperature with respect to time. The temperature, as you would recognize, it gradually approaches the room temperature where the glass is placed. The temperature is another limit as time approaches infinity. Both Isaac Newton and Gottfried Wilhelm von Leibniz, who independently invented calculus, introduced limits as their primary foundation of all calculus. It can be simple to understand as we go on with further explanation. However, once missed, could be a race failure. The value of a limit exists whenever the actual value of the function is undefined. However, not at all times could the limit exist in a function. There are actually other times where it does not exist. But saying that, we're going to move first with the basics of a limit. We have an expression of a limit today on our screen. This is actually read as the limit of the function f as x approaches a is equal to L. It can also be read in these two ways. Could either be f of x approaches L as x approaches a, or as x approaches a, the limit of f of x is equal to L. Notice that instead of x equals a, it becomes x approaches a, represented by an arrow, not an equal sign. That is because always bear in mind that limits do not care whatever is happening at x equals a. What matters is what value the function approaches as it comes near a. There are actually two kinds of a limit, the one-sided and the two-sided limit. Let us first begin with the one-sided limit. A one-sided limit is made up of two components, the left-handed and the right-handed limit. The left-handed limit is a limit that always comes from the left side, which is from numbers less than a. It is usually represented by a negative superscript after a number to signify that it comes from the left side of the point of concern or undefined point in a function. The framework of a left-handed limit looks like this, with negative 3 as a, where it is read as the limit of the function f as x approaches negative 3 from the left. For example, if we are looking at the graph of this function, the left-handed limit will always be observed on the line preceding the point you see on the graph, and those points lie beneath the numbers on the Cartesian plane before you open dot. In this case, the left-handed limit shall be from numbers negative 6, negative 5, negative 4, negative 3.9, negative 3.5, up to the closest number to negative 3. Could be negative 3.000001 or much smaller than that. So as x approaches those values, the values in our function get closer and closer to 9. Thus, the left-handed limit, or the limit of the function f as x approaches negative 3 from the left, is equal to 9. In a table of values, on the other hand, this can also be observed from the left side, or from above if the table runs vertically. Next is the right-handed limit. This is the complete opposite of the left-handed limit, represented by a positive sign, and it comes from the right side of a. So if that is negative 3, it comes from values greater than it, such as negative 2, negative 1, 0, 1, 2, and more. Definitely coming from positive infinity down to negative 3. In a table of values, this can be observed below the undefined number in a vertical table, or from the right if the table of values run horizontally. Using the graph a while ago, you can perceive that as our x approaches negative 3 from 2, 1, 0, negative 1, negative 2, up to negative 2.9999, our values get closer and closer to 9, which is just the same answer with the left-handed limit. So the limit of the function f as x approaches negative 3 from the right side is also equal to 9. Now, once the left-handed limit and the right-handed limit have the same values, then the actual limit, or the two-sided limit, would therefore exist. Why is it called the actual limit anyway? Well, the two one-sided limits are only there to check if a limit exists, and so if they don't approach the same value overall, therefore, it would be grasped that a limit does not exist. If we talk of just the limit of the function f as x approaches a without any sign as its superscript, then that is actually the two-sided limit, and its value is also just the same as the value of the left-hand and the right-handed limits. Going back to our answer with the right-handed limit, which is equal to 9, comparing this one together with the value we got from the left-handed limit, we can eventually conclude that a limit exists, and so the limit of the function f as x approaches negative 3 is equal to 9, as both limits approach the same value. Let us try identifying the limit on another set of examples. So right now you can see here a graph of f of x, where f of x is actually equal to the quantity of x squared minus 8x plus 16 all over x minus 4. You can also see here a straight diagonal line, supposedly that's a straight diagonal line, and with a hollow dot here, or a hollow circle here in the center. This hollow dot actually means that the value of this function, when given the value of 4, is actually undefined. Why? Well, if we substitute all the x here with 4, so definitely the value would then be f of 4. But just by looking at the denominator, the x in the denominator, when you substitute that into 4, the denominator then would be 4 minus 4, and that will be equal to 0. And you know that any number divided by 0, whether that's 1, 2, 3, 4, including 0, it will give us an answer of undefined. And now, since the value of this function is undefined, we put here an open dot. That's only for 4. But if we talk of f of negative 3, f of positive 2, and values greater than 4, such as f of positive 5, f of positive 10, they all have values. They all have definite values. That's actually the reason why we have an existing line here. This means that all the values here before the dot and all the values here after the dot all are defined. So let's say, for example, this 3, f of 3. So whenever the function is substituted into 3, it has a corresponding y value. Also same here with f of 1. It has a corresponding y value. So I represent here closed dots to represent that they actually have a value. There are also some graphs that you can see in the future where they actually have an open dot and a closed dot, and that closed dot lies outside the curve or the line. This also means that this is their actual value. But since we're only caring about limits, we talk about this undefined value along the curve or the line. Now, even though that f of 4 is undefined, we can still identify its limit. Now let us identify. You're going to first identify the limit of f of x as x approaches 4 from the left side. Now, since it's coming from the left side, it comes from the values less than 4, such as 1, 2, 3, and then 3.1, 3.5, 3.7, 3.9, 3.999. So as x approaches those values, going to 4, our function's values are getting closer and closer and closer to 0. So then the limit of f of x as x approaches 4 from the left side is equal to 0. Now let us try the limit of f of x as x approaches 4 from the right side. So this time, it would be coming from the numbers greater than 4, such as 5, 6, 7, 8, and more. So it approaches 5 down to 4.5, 4.1, 4.0000001. So as it approaches those points, the function's values get closer and closer and closer to 0 again. And so this limit is also equal to 0. Now, since these both one-sided limits actually have the same values, then therefore the limit of f of x as x approaches 4 exists, and its value is equal to 0. But bear in mind that f of 4 is still undefined. So right now we have here the table of values, which consists of 2 rows, wherein the first row actually contains values that belong to x, and the next row consists of values that belong to g of x. Now, for x, we have here values such as 7.89, 7.9, 7.999, 7.9999 until 8.1. Well, for g of x, we have here values such as 3.79, 3.89, 3.999, 3.9999 until 4.3. Now, in the center of the table, you would notice that there are actually values missing here, such as for x, we have here 8, and for g of x, we have here 4. However, the function's value whenever x is equal to 8 is actually undefined at this point. So all we have to do then is just to identify the limit. In most cases, teachers would be asking you, what is your reasonable estimate for the limit of g of x as x approaches 8? But others simply ask, what is the limit of the function g of x as x approaches 8? So they're just the same actually. As x approaches 8 from the left side, that is from 7.89 to 7.9999, the function's values get closer and closer to 4. So as you can see, there's that 3.89, 3.999, 3.99999. And same from the right side, from 8.1 down to 8, the function's value get also closer and closer and closer to 4. So
since they approach the same value whether from left or right side, the limit of g of x when x approaches 8 exists. And the value for the limit of g of x as x approaches 8 is equal to 4. Now let us solve for the limit of h of x as x approaches 3, where the function h of x is actually equal to x squared minus 6x plus 9 all over x minus 3. But before that, let us first solve this actual function. H of x is equal to x squared minus 6x plus 9 all over x minus 3, where x is equal to 3. They both have different answers, and they have different ways on solving them. So let's first solve this. We have here h of x. We're going to substitute only the value of x, which is 3. So that is 3 squared minus 6 times 3 plus 9 all over 3 minus 3. And then we would have 9 minus 18 plus 9. And then 0 in the denominator. And so in the numerator we would end up with 9 minus 9, which is actually also equal to 0. Which is actually 9. We'll end up with 9 minus 9, which is also equal to 0. So 0 divided by 0 is not actually 0, but it's definitely undefined. But here, for the limit of h of x as x approaches 3, the same value of the function, so here, instead of substituting it directly, we're going to first factor the numerator out. So instead of x squared minus 6x plus 9, we're going to make it in the ways of the squaring of a binomial. So that's actually supposed to be x minus 3 squared. But we're going to remove that squared and we're going to expand it. X minus 3 times x minus 3 all over x minus 3. And then we're going to cancel the ones that are the same. And now since there's only one x minus 3, so we're just going to cancel also one x minus 3. Even if there's also an x minus 3 here. Alright. Then actually we would end up with the limit of h of x as x approaches 3. Instead of the function a while ago, it becomes then x minus 3 only. Alright, now this is the only time where we can substitute x by 3. Alright, now it becomes 3 minus 3. And it goes 0. Now see how the answers differ from each other. In the first part, when we substituted the values, the answer was undefined. Well, when we talk about the limit, the answer is 0. So if we graph those answers, it would turn out like this. The function h of x goes as a straight diagonal line, and as it gets to 3, it becomes a hollow dot because it is undefined. However, when you talk about the limit, it would actually approach to a certain value in the y, which is 0. And also same with the right side, which also approaches 0. And now since they are the same, definitely the limit exists and the answer is 0. Even if the function is undefined, we can still identify its limit, its estimated value of the function, which is 0. Now let us examine this two table of values. Now instead of one, there are actually two table of values. That is for you to be given a much clearer explanation about how a two-sided limit does not exist. So here we would talk much about 2 in both of these table of values, because these two table of values are actually connected to each other. This table of value right here gives us values coming from values less than 2. So definitely we would say that coming from as x approaches 2 from the left, so from 0 to 1.9999, the function's values get closer and closer and closer to 9. However, this table of value right here, which gives us values coming from numbers greater than 2, and so they approach 2 from the right, from 3 to 2.0001, the function's values get closer and closer and closer to negative 6. So instead of 9, it gets to negative 6, which means that they do not equal each other. And therefore, since the two one-sided limits do not equal each other, this means that the limit of g of x as x approaches positive 2 does not exist. And definitely, if we talk about 2 not with a negative sign or a positive sign, this actually means that this is a two-sided limit. Okay, now the two-sided limit g of x as x approaches 2, or simply the limit of g of x as x approaches 2, does not exist. Now, in order for us to see better, let us talk about this graph right here. This is actually the graph of the same function. Now, you would see it from here that this red dot right here and closed circle right here, they both point the same value here in x. And now, you'll see that as x approaches 2 from the left, you'll see this line right here, it actually gets closer and closer and closer to positive 9. Well, if x approaches 2 from the right, you would see how the function's values get closer and closer to negative 6. And that's the reason how the two-sided limit g of x as x approaches 2 does not exist. So right now we have your three graphs. And these three graphs will tell us how could the limit not exist. Now let us first evaluate this graph that you can see right here. Now all of the function's values here all have their corresponding limits. They all are defined for each other for each value in the x-axis, except for one value, that is 2. Now, all of the limits here along this curve and along this curve that you can see right here on the right are all defined, except for one value, and that is 2. Because as you can see, the curve is discontinuous. When you say discontinuous, that means the lines don't meet each other. Instead of continuous from here up to there, it gets towards here. Now, as x approaches 2 from the left, for example, our function's values get closer and closer to 3. While as x approaches 2 from the right, our function's values get closer and closer to what appears to be 0.5. Now, since both limits don't approach the same value, then in conclusion, the limit does not exist. However, for additional information, if we're finding for the value of f of a, or the actual value of the function, we have this closed dot right here, and that's actually its value. And so the actual value of the function is 0.5. That's how a closed dot helps. And this open dot right here is not actually the actual value of the function. It's a hole in the graph, and it is actually where the graph is supposed to be continuing from here up to there, instead of here up to there. Now let us evaluate this one right here, this next graph, where the curves are forming a vertical asymptote towards 0. Now as x approaches 0 from the left, you can see that our function's values are headed towards positive infinity, while as x approaches 0 from the right, our function's values are headed towards negative infinity. Now we are only identifying here a limit that is present in a number, whether it could be an estimated value or a number that is also the actual value of the function. But if the limit provides a value which is, for example, positive infinity or negative infinity, then automatically the limit does not exist. However, for other numbers, such as, for example, negative 3, they both have limits. They all are defined for each of the function's values in the x-axis. However, Only for 0 is the one that's not defined because we do not know. Maybe this curve right here is headed towards positive 10 million. However, for this one, it's headed towards negative 10 million. We do not know. But even though that let's say for example, suppose that they approach positive 10 million and this one is negative 10 million. Still, the limit does not exist because they both approach different sides. Lastly, we have this graph right here. And instead of forming a vertical asymptote towards 0, it forms a vertical asymptote towards 2.1 in the x-axis. Now, as x approaches 2.1 from the left, our function's values are headed towards positive infinity, and same as to the right side, it is also headed towards positive infinity. However, they do not get to meet at the same point. Or if ever they would be, we do not actually know what could be its value. So, as they are both headed towards positive infinity, and since positive infinity is present in both of the one-sided limits, then definitively the limit does not exist.
So that's it for this episode of Math Magic, particularly in Calculus Begins. I hope you guys learned a lot. Well, all in all, we have learned about the limit, especially to its applications, its importance, and also the basics of a limit, which consists of how do we identify the limit of a certain function, and how do we identify the limit from the left side and right side, and also the two kinds of limit, which are actually the one-sided and two-sided limit. See you again in another episode of Math Magic. My name is Ehron. Stay safe and keep following Math Magic. Bye!